Hi everyone, welcome to a new session. We're coming through the third session in order to bring an AlphaCode to open source version of it from the paper description. So the last time we just started generating those codes that we're gonna try to cluster and filter. So I guess today we're gonna be clustering mainly. Let's do something like cluster code or code cluster .py, and basically how it's gonna work, we're gonna run the data processing, then the code generation, and finally the code clustering. So haven't done anything since the last time, but basically I'm just gonna save this LLM stick to a file, JSON file, and we're gonna be opening it on the code cluster. Alright, so let's do it now. Let's try to refresh everything we did last time. That's gonna be something like JSON dot dump, and we need to dump the LLM stick, and we're gonna save it on open. That's gonna be something like gen code. So basically gen code code.json, something like that, or data.json. This is gonna be open as write, and that is basically it. So let's try to run it again. We're gonna be needing yeah, I don't know why it doesn't work today. Oh, I guess I know. Alright, so one of them is already open, and just let me copy paste right. And so we had two models, if I remember right, and one of them was this one. Alright, okay. Yeah, let me save this one. Let me save this one as well, and we have everything set up as the last time. Okay. So run open enemies neural. Yeah, so basically this, which were the models that we loaded the last time? Oh, this one and this one. The neural and this one. Oh, they're right here. Okay, so one thing we need to do is just change the port of this one, because this one is now running on 8080, but that's basically it. Alright, so I guess we can just try to launch this code, see what happens. We can use this as a summary from the last time, and I don't know if we have loaded the JSON. Yeah, we have JSON right here. Alright. This possibly is gonna take some time. Yep. So how I think Llama CPP works is it will try to catch any previous generation that it had or prompt, and in some way it's gonna be faster. Like if you send the same prompt multiple times, if it's gonna be catch, and just because of that we are running the first time and it's the slowest that we're gonna experience through the video, and basically the next ones are gonna be faster. I think they catch something on it. So we're gonna leave it there. We're gonna start thinking about the code clustering process. So I don't know a lot about clustering, but I think we can start with something simple, like string similarity clustering. This is a great post, Yazin, and he provides a lot of different ways of measuring text distance between two different strings, and I think that's gonna be helpful. You just don't need to take care of anything related with vectorization of them, and basically you just can put the text in there and it's gonna calculate them. So as far as I can tell, Jacquard similarity is quite interesting because it's basically token based. It's gonna try to tokenize everything, and basically depending on the similarity of the tokens, it's gonna give a different value. And as far as I can tell, we can also use sourcing. Yeah. Overlap similarity, I don't think this is gonna be huge, because the code is likely to have differences. Like if we ask it to generate the code twice, it's very likely that they're gonna use different variable names, it's gonna use different amount of spaces in between. Code and similarity is gonna be fine as well. So we're gonna start simple. I don't want to battle this n-gram similarity, to be honest, because that's huge. I don't think it's gonna give any value, just to get it started. So yeah, Jacquard is gonna be fine, and cosine is gonna be fine. Jacquard and cosine. So I'm gonna start with them. Yeah, and we're not gonna give it the vectors that are returned by Llama CPP or anything. We're just gonna send different strings, and we're just gonna leave it to do whatever it needs to do with them. It's gonna be simpler. Alright, so this is basically, we need to import this text distance we're gonna calculate this one. Because as far as I can tell, they don't say how AlphaCode clusters. Yeah, they don't say which algorithm, so this could be basically anything. We could do something like supervised learning as well with scalar. Yeah. Well, we can just bring together many different metrics and possibly just bring a mean of all of them and see what happens. Because we're gonna give it some code, it's gonna generate some clusters, and we're gonna have a list of clusters. So of course we're gonna need scalar. And I don't know if they give a certain amount of clusters or the number of clusters is just calculated, because we have from all the different clustering algorithms we have different that are you give it the number of clusters that you want, and others just basically calculate that. So you can see k-means just basically give it the number of clusters, but for example affinity propagation doesn't. dbScan you give a size of the neighborhood. I think dbScan is gonna be huge, because we can just generate the number of clusters by just telling, hey, from all the different generations I want no more than 3 neighbors in the same, like try to find distances so that no more than 3 neighbors are on the same, or x number of neighbors. Optics also seems great, because we can tell, hey, I want a 30 minimum in each cluster. Don't try to generate so many clusters. But k-means is usually the most common, right? Like k-means. So let's do it. So it's gonna give us, if we ask for the labels, it's gonna give us the labels. We can give it the number of clusters, and basically it's gonna give us, hey, these these first three values are in the first cluster, these three next are in the second. So we need a way of getting the different codes from a cluster, right? So let's do something like the good part of it is we can train the clustering algorithm, and we can do it on two different ways. Like, we could do three ways of clustering. We could have cluster by string similarity. We could do cluster by vector, row vector data. Or we could do both of them. So how I usually see it is, the easiest way to do it is you basically calculate the string similarity between all the different pairs, you choose that, and then basically cluster based on that. So if you have, for example, a string similarity of 3 between two of them, and then a string similarity of 6, I'm just making it up, you're gonna have those from 6 on a 30 cluster, and you're gonna have both from 3 on another cluster. And in this manner, you can have clusters with more disparity and clusters with less disparity, like similar. And in this way, you can just, if you want to generate, or if you want to choose something that has more temperature or something that has more creativity from the LLM, you could use that cluster with a higher amount of, or less amount of similarity, and use the more similar ones for less creativity. But I think this is the simplest way, because you're just gonna have different values, and those different values are gonna be used for the cluster. But if you choose the vector data, you're gonna have different values on each element of the sample, instead of just integers. So yeah, I think we're gonna start with the raw vector data. Yeah, that's gonna be great, I guess. This is still generating, so we just need to keep waiting. And then we have, this is string similarity. And this cluster algos. So we're gonna be using k-means for sure. And then dbScan is something interesting. Because you give it the neighboring size of each component. So by just giving that, you can just say, hey, I want more granular clusters, or I want more general clusters. Because if you just choose the amount of clusters, it's gonna try to just group everything together. But by using dbScan, you can just say, hey, I want more variety, less variety, all that kind of stuff. So if we want to use, for example, it's still generating. So if you recall, we gave it 3 different values for temperature. I think it was 0.8, 0.7, and 0.6. And then we gave it 10 different problems. And we have 2 different LLMs, so it's gonna make 60 generations of these. Yeah, I don't know how much time. I should have done it before starting the video, but whatever. So get code from cluster, and we give it an ID. Yeah. So we need to use k-means. And it is likely we're gonna be using fit predict. So I'm not making like training set and test set and see if whatever we learn from the training set we can extrapolate to the test set. Like these days there's a lot of chatting and a lot of memes and a lot of all that kind of stuff regarding that you shouldn't train on the test set. But there are occasions in which you just have no separation between them, because what we're trying to do in here is we're just gonna cluster, see the different clusters, we're gonna choose the best from different cluster, and we're gonna use those different values or those different samples as a potential answer. And it's very likely that if we start solving problems regarding, I don't know, I'm just gonna say PyTorch, and then we start solving problems about Pygame, those different things are gonna be so different. So there's no point on trying to train a model on a first training sample. Of course, you could choose a very general sample with values from all the different kinds of problems, but you want to have a lot of granularity when you're using the answers, when you're basically just separating between the different values that you get from the LLM. So I don't think there's gonna be a separation between training and test set. It's gonna be just give me the clusters. I'm just gonna choose these values. I'm just gonna evaluate them. We're gonna see how them, and that's gonna be it. So we're gonna go for fit and predict together on the whole data set. Alright, so this finished. We still have data.json. We do have it, okay. We are not gonna just open it up. So this is data, JSON load, alright. So for LM in data, right, we're gonna have like x equals this. And let me check. So we have the model. We need to cluster the different generations from the same model, I guess. Or yeah, let's get just all of them together. So we're gonna traverse, we're gonna choose gen, and we're gonna choose code. Model, yeah, for each model. sorry, my mistake. So something we need to do before we do the k-means, and of course, as far as I can tell, k-means is going to expect all the different values to have the same size. Like all these need to have the same size, so all the different codes need to have the same size, and that's going to be the biggest amount of how's it called, tokens that you can have in your context window. We're gonna pad on the end. I think we're gonna use, well, the padding, and we need to have a way of clustering. So I think the best way to cluster is by using BERT or something similar instead of using llama and all that kind of stuff. Basically, because when you do search or when you do RAG, it's very likely you're gonna be using a BERT model, to find out where the different values that you're looking for are in the text. Because the encoder is better, because the BERT model, as far as I can tell, is an encoder base. I don't know if it has a decoder, but it's encoder base for sure. It has an encoder, so there's more rich amount of values in the latent space than if you just use llama. So yeah, we need to use BERT, generate the tokens, bring them. Yeah, let's go. So Hugging Face BERT burn case. This is possibly not the best encoder because I don't know if it has Python code in order to generate the different tokens, or if it just makes them whatever, but we can use it. I don't think we're gonna be using the model as a tokenizer. Okay, these are the different values, and we need to give, so we have input IDs, we have detention mask, we're not looking for detention mask for sure. We have input IDs, token type IDs, we're gonna skip that, and we need to check for the input IDs. The rest is something for the model, so let's get this done. Alright. And these are of type tensor. Like, possibly we should get the value inside. I don't know if we have something like toList. Yeah, that's better. And possibly we're gonna just be choosing the first element because it is a list of lists. So I don't know how the sklearn will expect that. Yeah, we're just gonna take the first element. Yeah, seems great. So expectors, we're gonna take them in here, and it's gonna try to create 2 clusters. Let's be more like 5. Print k-means dot labels, I think it was. Yeah, so we need to pad at the end. We need to get the maximum size of it. So I don't know if this is going to work, but let's check what it creates. Like, yeah, basically just giving the path token, which I just guess is gonna be 0. So let me change this for path token. Yeah. And support operand times for alright. I think this will work now. Alright. Oh, because we just gave it fit predict. So yeah, we should possibly use fit only. Yeah, it's gonna give us the numpy array instead. Yeah, so these are the clusters for the different codes. So all these things in here for the first cluster, then 2 for, yeah, this doesn't look like rate at all, because pretty much everything is going through the first cluster itself. So possibly using the bird tokenizer isn't the best thing. So we can try others. Like I have said before, we're not gonna be using llama, but possibly that's the best one we can use. So llama, look at OpenEMIS. We're only gonna be using the tokenizer, so I don't care a lot about the model being downloaded and all that kind of stuff. Looking for an example, basically. And these are clusters. Now, yeah, I find them better, to be honest, like more variety. But we should test that on, I don't know, they don't even say how many clusters Google is using. A scoring model which will be used, yeah, biggest code sample clusters. So 10 biggest clusters. But we don't know how many clusters we're gonna be looking at. Yeah, that's something we don't know. I guess we should look at the code and see if we should just put all those things in the same one. Yeah. Like we have 10 different problems. So possibly we should use 10 different clusters. Yeah, possibly. Let's see. Alright. Let's leave it there. That's gonna be our clustering way. That's something we don't know. And let's let's just consider that we're not gonna be just doing Jackar now and yeah, all that kind of stuff. Let's see what happens with k-means and we move on. So basically, let's finish this code. So then yeah, let's see the values on the cluster number 2. Well, I don't know if there's there's only one, so let's get them from cluster 0 better. Sorry. Alright. Alrighty, but we need to bring it back to code, right? So, yeah. Mm, or possibly using the code. We're gonna get there. Yeah. Token answer the code. Yeah. There you go. So I would like to see, oh, from the same one, right? We have a lot of unknowns. So, what happened before? Like, why couldn't we just get the same values when we just so? Yeah. Yeah, great. So these are the codes on the same cluster, which seems reasonable, right? This is very likely to this one. And then, yeah, they're basically doing things with arrays, so this would be, I guess, on the same cluster. So yeah. Now the thing is, we need to differentiate. Like, if we're gonna give it a problem, we need the solution, right? Instead of just giving all the problems, get the solution. So let's do it now. Um, Something we can do is, so they're saying here that they're gonna use the 10 best clusters. Oh, each candidate of the 10 biggest code samples clusters. So it's giving us something like something we could use is, let's get the 3 best clusters, for example. Alright. So we have the number of clusters, the tokenizer we're gonna use, we have the data. Now we need to choose only part of the data. So instead of giving all the data, let's choose, for example, a problem. Problem is gonna have an ID, and we need to get the output from all the models. So problem ID is gonna be it. Yeah, only the first one or whatever. So equals ID. Yeah, that sounds great. And now let's do something more. So yeah, let's do it. So have all the codes. Yeah. So Alright, so we basically have it now. Um, yeah, it is pretty much completed now. Something I'm gonna do is I'm just gonna comment many of these things in here that we don't need them. So this, oh sorry, yeah, 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 all these things out, and out. And now we just need to get the best solution for the classes. So okay, clusters, and I use that. Well, that's different. So that's gonna be 3 and clusters, sorry, and then we're gonna use the best. Yeah. So something I wanna do is print instruction. Um, so problem ID. Yeah, let's go. Oh. All right. Code. Hmm. Yeah, we only have 2 generations from that, but that is possible because we have separated the temperature. Like yeah, from this list we have temperature. So that's interesting. Yeah. So what we're gonna do is, oh, all right. Let's do something. I'm just gonna copy paste instruction. And that's gonna be it. Alright. Alright, so we have 5. We couldn't have more. Yeah, makes sense, right? Because we have a problem, we gave it 3 different. So yeah, makes sense. 7 clusters gonna be something like, we're gonna calculate that, and then clusters gonna be like n clusters equals length of codes divided by 2. Right. And we're gonna give it an integer. Yeah, great. So these are the different clusters. Instruction create, this is instruction, right? And this is code of cluster 0, right? So now we need to get the biggest cluster. For example, let's say we want to get the biggest cluster. Alright, we can get help from biggest cluster. Alright. Yeah, but I don't want this. I want the actual solution. So what is the biggest cluster? Biggest cluster is, let's say, 1.